Hi everybody, this is Michal from Airhead again, and today we will talk about the principles of flights and more specifically the topic of controls. So we will go through 5 of the most recent questions from the topic, and all of these have been seen across all the EASA authorities in the last 30 days during the actual ATPL exams. So I hope this will be helpful. We'll dig a bit deeper into the questions and the answers as we always do. And if you have any questions, feel free to write a comment and we'll try our best to answer them as quickly as we can. So let's just jump into the first question without further ado. And which of the following affect the setting of the stabilizer trim for takeoff? And so this question is very practical because in the future, as you'll be flying the big jets that use the THS, you will actually need to set it before takeoff. Of course, in order to make sure that the proper control forces are required during this critical phase of flight, and as well for the nose of the aircraft not to lift off uncontrollably before you would like it to do so. And in order to set these streams and prepare everything, you'll be given a load sheet from the loadmaster after the aircraft is filled with passengers, and this will have all the loads in there, and as well it will have the recommended setting for the horizontal stabilizer trim. However, also you will need to input all the data into the MCDU, and the MCDU, which manages the FMGC in the aircraft, will actually ask you about the flap settings, about your actual takeoff mass, and also your CG position, both zero fuel weight and the actual one. So these data will be there in order to do exactly this, in order to calculate the stabilizer trim setting for the takeoff, and the system then will give you the value which you can use and input before takeoff. So this is a very practical question, and of course the correct answer here will be the flap setting, the CG position, and the actual takeoff mass, as they will all influence the moment that the aircraft will create during the takeoff. The outside air temperature is not that important. Of course, it will change the thrust that the aircraft will generate. However, it is not that significant. And remember that in some aircraft, we will use actually the flex takeoffs, where we will trick the engine into thinking that the temperature is different than it actually is. So these temperatures go into play a lot here, and this would not really matter when it comes to the settings of the THS. And now for question number 2. So which of the following statements about tailplanes is correct? A T-tail is. So of course we have two general types of the tailplanes, and we will have a T-tail and the conventional one. And the T-tails are great because they are able to generate more forces, because they have a greater moment, because they simply are further away from the CG, as it opposed to the more normal and conventional one that we see on most of the cat aircraft. Um, However, a T-tail, and this is something to remember well, has some disadvantages. And of course, the main one is that it is much more susceptible for a deep stall, because as the aircraft wings stall, all the turbulent air that is left behind actually hits the tailplane when it is in the T configuration, making the elevator almost completely unusable. So the recovery is very, very difficult, if unfortunately not impossible. So going into the answers here, of course, a T-tail is more stabilizing than a low tailplane. This is why, because it's less affected by the downwash behind the wings. And of course, the downwash, as you should remember from the previous topics of principles of flights, always goes down, because just as the vortices, they are going down below the aircraft, and so does the downwash. So when you're flying, of course, the T-tail is positioned higher, so further away from the downwash, rather than the low tailplane. And this will give it a more stabilizing probabilities, and this is mainly because of a larger moment. And now for question number 3. So a horn balance is a control system and has the following purpose. So the horn balance is something that will alleviate the forces on the controls, because it will use some of the aerodynamics in order to help us manage the controls. And this is very useful, used mainly on the GA aircraft, however, not necessarily only. And here for this question, is something that is worth remembering, and that is to obtain mass balancing answer here. And it is important to remember that the mass balancing is done to prevent flutter. And so if you see flutter, always go for the mass balancing. And if you see mass balancing in a question, then flutter will most likely be the correct answer, as this is the general principle to prevent it. And of course, the horn balance will decrease the stick forces, so it will be easier for us to fly certain controls deflections, um, as the horn balance will support using the aerodynamics in our advantage. And now for question number 4. So a transport jet is stabilized on approach in the landing configuration when a vehicle enters the runway. As they initiate a go-around, the crew discover that the stabilizer trim is jammed. What is the effect on controllability? So of course, remember that primarily a trim is always valid and correct for a given speed. So anytime you are in a trimmed aircraft, and if you start accelerating or decelerating, you will 100% need to change the trim settings, because the aircraft will now be in a auto trim position. And the keyword here is that as the aircraft accelerates. So of course, if you just fly a go around and you do not change your speed, then most likely there would not be that much of an effect. However, uh, with most of the aircraft, because here we also should consider the fact that the engines will have a great moment, especially the underwing engines used in most SCAD aircraft will generate a high nose-up moment. However, not thinking about this right now and not making any assumptions, just remember that as you accelerate, you need to change the speed, and also as you decelerate. So here, as you are going around and as you accelerate, you increase the lift, and in order to uh, and this increase in lift actually will make a nose go up. And going into the answers right here, then aircraft's nose will tend to rise as the aircraft accelerates, and this is absolutely true. And you'll see once you start flying, or if you already have started flying, that once you accelerate, the aircraft will always want to go up. And this is true no matter the phase of flight, as of course during a go around, although you're climbing, in some cases you will still be accelerating to a set speed. So make sure that your aircraft is trimmed properly. So if you go around with a jammed stabilizer, then you will need to input some nose down on your controls in order to fly safely and for the aircraft to do what you want. And now question number 5, which is the last question and that we are going through here today. So on an aircraft with partially powered flight controls, which of the following provides the greatest force to control surfaces? And of course here, the correct answers will be the hydraulic system, as in the partially powered flight controls, as it is with some manufacturers like, for example, Boeing. We will have the pilot's inputs that will do some movements on the controls. However, these will be amplified using the hydraulic system, because pilots are not able to produce enough force to overcome the aerodynamic forces when you're flying big jets, moving big control surfaces at the cruising speeds of 300 knots and more. And here also remember that there were 3 general types of these controls. Of course, we have the mechanical, that we're using the push rods and steel cables, as it is with most GA aircraft. Then we have the partially powered flight controls, which are used in the cut aircraft, for example. And like I mentioned before, like the Boeing. So in this case, the pilots will feel some of the feedback, aerodynamic feedback on the controls, as they do need to overcome some of these forces themselves. And also these will be reversible because you have the feedback back on the controls from the control surfaces. And as you move the control surface, also the yoke will move in the cockpit. And then lastly, we have the fully powered, which we can also divide into the flight-by-wire system, that are both fully powered. The fully powered systems will provide no feedback for the pilots when it comes to the aerodynamics and the movement of the controls and the feeling on the stick. So these are the 3 general systems, with the 4th one being the flight-by-wire, which uses flight computers in order to move the surfaces as the pilot requests the G loading or the roll rates, rather than the specific deflection of the control surfaces. However, this will be it for today. So a quick session talking about the principles of flights. I hope this was interesting and somewhat helpful. If you have any questions, as always, feel free to let us know in the comments. I wish you all the best with your studies, and I hope to see you in the next video. Bye bye.